Good morning. So, as Professor Mahapatra said, that this is going to be an informal session. So, please stop me. And I wanted to make you sort of, go through the journey of this 3-nitride semiconductor. And it's especially there's a purpose to say not to as a compound semiconductor, but to say the 3 nitrides, which I've been sort of working on last 15 years. So, let me start here. How many of you have seen this person or know this guy? How many of you? Okay, so he is Mr. Suji Nakamura, the person behind this all solid state lighting that you see, LED. So I'll tell you a very interesting story about this person. Yeah, so he's from a very small, tiny island in Japan. Okay, so unprivileged, no facilities, no degree. He was from the 2nd or 3rd tier university in Japan because he couldn't get. He was very poor in studies, traditionally to be called. Okay. So you see this for a very, and when he started working on these 3-nitride semiconductor or gallium nitride, he was 36 years old. Okay. Now, on the other hand, there is another person, so you see, Herbert Paul Maruska. So no one knows him. And he was from Stanford University. He did PhD from Stanford University, working on gallium nitride, so trying to solve the problem of material quality, trying to improve the material quality. Okay, so the destiny took them to different places. I'll talk about that. Yeah, so just to tell you what has happened to Suji Nakamura after 20 years or 25 years, he was one of the 3 Nobel laureates awarded for their work in finding out a process technology. This was the first time in the history of the Nobel Prize someone was given a Nobel prize for figuring out a process. Then you realize this how critical is being to grow those material, for examples. Okay, so but let me go back to what Suji Nakamura did. Okay, so Suji Nakamura, when he got the Nobel Prize and he became famous, of course, and then the journalist asked him, what was your motivation? What motivates you to drive this? What was Suji Nakamura's answer? This is what it is. This was by being always angry. Yeah, so this is what it is. I mean, still he says that, being angry drive me, for example. So my incentive in research is always an anger. But there is a background story behind this. This is what you should all know about. So this inventions, right? This is these 3 persons. Yeah, everyone has seen, for example, this one. So right after the invention of the transistor, then the people who are looking for some other material applications, for example, one of obvious application was looking for the light sources, the material based light sources. So unfortunately, what has happened, or what was the reason, is that these all element that you find in the periodic table, like for example, the first transistor was made on germanium, then the silicon took over, but those are all elemental semiconductor, and unfortunately it was found that those materials were not so nice in terms of the emission of the light, for example. Optically they are not very efficient. Then the chemist played a very important role, material science played a very important role, and they figured it out that if you add some 2 elements from the periodic table, then you create a new material, and that material plays wonderful and some sort of the new material system that are optically much efficient or very strong light emitter. These are called the 3 gallium, and one of the gallium arsenide was the first material. So the gallium comes from group 3 in the periodic table, arsenic comes from the group 5. So that's why they're called 3,5 semiconductor. Now these are also called the compound semiconductor. The moment this material was invented, right, they figured it out that there's another system of material, then people started working on the applications. The first applications was sort of driven by then the flat panel display color televisions, right? So in order to make the color televisions, what we needed was to have these 3 primary color. If you have 3 primary color, then you can make it any color from these 3 color. So the first one, of course, these material, the way they emit, it's actually the emission wavelength is dependent on their band gap, for example. And then they were looking for a different material that would emit the red green and blue. That's an ideal situation. So unfortunately, gallium arsenide emits the red. So the red problem was solved. Yeah. So the Nick Holonaik, so the first LED was sort of made in 1962. The green and blue was still a problem. So the green was kind of made, but from an inefficient way. For example, gallium phosphide was actually the proper, if we just look at the band gap, has this exact wavelength which would actually which should be emitted by gallium phosphide, but unfortunately gallium phosphide was indirect band gap. So they did what? They added more arsenic, or if in a gallium arsenide, if you have a less than 45% or 50% phosphide, then it's a direct band gap. So this is what they made this first high brightness, the yellow light. So the combining these two, and then the last solution was the blue. So where was the blue? So blue was missing. The people are looking for different material. So what they were sort of settled down, the chemist suggested that there could be something called the gallium nitride. So if you take gallium and then take the nitrogen and mix them, get a new system which is called the gallium nitride. That's the typical way you think, for example. All right. So this young PhD graduate from RCA lab, in fact, he got a special scholarship from RCA lab to do his PhD on gallium nitrides to figure out how to improve better quality of a material that would emit the high efficient light, for example. Okay. So then after his PhD, he came up with a solution with improved material quality, and also the doping, for example. The doping was another challenges. So for example, those materials naturally are n-type. So if you don't do anything, it's a crappy system, but then you will have a large number of the electron in the system. So the p-type was always missing. If you have to know, or if you have to make the LED, you need the p-n junctions, for example. That's the best way to get an LED, for example. So he came up with the magnesium as a dopant. Okay, so this is the +2. So you replace gallium and then you get this hole, for example. That was the typical solution. That's the way the dopant works for silicon, for example. If you have a group 4 and then silicon, and then group 3 would create the hole, for example. So he came up with the solutions with an improved the quality of gallium nitride. He was very happy. He came to the with his boss, and he was heading the material research lab at RCA. And because there was a sort of a problem of improving the efficiency, so there was this very little business aspect to that. So it was not improving. Then they had this almost huge loss in the computer business and $250 million. And then because of that, the entire program in gallium nitride was shut down. There was nothing after that. So everything stopped. And what happened to, he came up with the solution with his PhD from Stanford. And you know what had happened? The destiny, as I said, took him different places. He was fired from the lab, from RCA lab. He lost his job. The entire program in US was shut down. There was no work on gallium nitrides or this kind of a systems in the United States, in fact, across the globe, except that one place is in Japan. So there was only one group which was pursuing. By the way, there was another material system which was sort of extensively studied in order to find out the green light solution, was a zinc selenide. And zinc selenide was easier to make, and many people in industry also started focusing on putting more attention to the zinc selenide material. There was only one group from the Nagawa University headed by Professor Akasaki and his young PhD student, Hiroshi Yamano. They were working. And the last paper, if you just look at it, was published in 1972 or 1973. And then between 72 and 83, there was no paper, no work. You don't find anything except the first paper came out from this group in 1986. That they figure out that there is another way to create this new material or gallium nitride, which was eventually will have the better efficiency, for example. Okay. So that just I wanted to tell you that figure. You see, this first LED was made on a MIAs because there was no p-type material, p-type gallium nitride. So it is something like metal insulator semiconductor based LED with an efficiency almost like negligible. Today you find an efficiency is 95%, 98% of this normal blue LED. Then what happened? Then the Nakamura, on the other hand, was, as I said, that he did not find any good job. His university education was poor, and then there was only one small chemical lab. He found a job that's called Nishia Chemical or Nichiya Chemical in Japan. And initially that company was mostly working on some chemical compound. But then when this work was sort of going on around the globe, then his boss, Nakamura's boss, called him and asked him to work on the gallium nitride or find a good green light solution, green emitter. And so, as I said, that most of the work was concentrated on zinc selenide. So then Nakamura was thinking, what should I do? If I work on the zinc, so this is exactly the motivation was. He wanted to have a PhD. That is wish. And then he thought, if I work on zinc selenide, there are so many people already working on. There is so much competition. And those days, I don't know today what is the criteria. In his time, the criteria for his lab was you have to publish 5 papers and then you get a PhD. Then he was thinking, which is the material that no one is working on? Then he figured out that's the gallium nitride. Then he started working on gallium nitride. He convinced his boss, in fact, the director or even the founder of this Nishia Chemical, and asked him for like a sort of 5 million grant for this one. But this previously, what was happened, he was always failing. He was not doing well. He couldn't get any sort of revenue to the compound. He was frustrated. He thought, today is my last day to the company. I just wanted to see if it works. So he went to his to the founder, asked for $5 million that time, and to his surprise, because the other people had no idea what semiconductor was, and then he was granted $5 million. It was half of the revenue of that company. So that was a gamble taken by the founder. So then he went to understand, to know how this technology work, how the process technology work. He went to University of South Florida in US. And once he landed there, then he realized that the machine he was supposed to work on, it did not arrive. Then after some time, the machine came, the MOCVD machine, but he spent 1 year just to sort of installing that MOCVD machine. He couldn't do anything. So he was very frustrated. Then he came back with this understanding that he would have to do everything from the scratch. He started working on this, building this MOCVD system. And every day, so he works on some kind of design, and then at the end of the day, he realized, or there is some kind of leakage of these gases or some chemical, and then there's going to be some kind of explosion in his lab. This was the everyday story when he was actually working in Nishia Chemical. And so the people initially were sort of very worried what is going on. People got scared, and then they started making a fun of him, right? Look, this guy, he's this explosion guy. And this is exactly why I said the innovations by anger. He was always sort of bullied in his lab. And then people start, that because this was like everyday story, people stop giving any attention to this, what is happening. Oh, that's this the Nakamura's lab, there's this explosion. So that's a story. Okay. Then after 3 years of intense struggle, then he figured out the solutions where he sort of made this very high efficient blue lighting the diode. But what I'm trying to tell you that, that partial solution was already figured out by the Akasaki and his group. But this is the man who took it to the next level. He found the solution for not only improving the quality, also the solution to figure out the P-type gallium nitrides. Without P, you won't be able to make the high sort of efficient LEDs. Not only that, because he was working on industry and he was working so aggressively that he convinced many people to take his solutions, and then many people started working on this gallium nitride, and eventually today you see the result. So the implication is unprecedented. For example, it was because this guy was so sort of aggressive in his solution, in his technology, So he convinced everyone to switch from, for example, incandescent bulb to the LED bulb. Now you see what the implications. So today, if you go to the supermarket, you will find the LED bulb, for example. And if you notice that the power that it consumes, it's extremely small, 3, 4, sometimes 8, 9 watt. But early days, 20, 30 years back, so those bulbs were not made of the solid state material. They were having some kind of filament, and that was extremely inefficient. So only 30% of 100 watt, if you spend, you will get equivalent of 30 watt sort of a light. So that's the kind of the change you have seen. Now this another figure people sometimes so don't pay any attention, because it has become so obvious that LED bulbs are omnipresent everywhere. Okay, so now you see the energy saving. So we are talking about the energy saving when you are making the memory high sort of speed, the computer. One of the motivation is to basically save the energy. Now we think about moving from the filament bulb to the solid state lighting, or even the LED bulb. So in India particularly, our Ujala program, if you see, so we have almost like a 4,800 crores kilowatt hour energy saving annually, 48,000 million kilowatt hour, and that would translate to 19,000. Now it's, in fact, it would be like 25,000 crore of savings from the consumer. Think about the number, and that add to, for example, 30 to 40, even today is more. This data is almost like 6, 7 or 1 year old. It's like 30 to 40 million tons of the CO2 emission was being sort of avoided annually. So this number speaks the significance of this technology. Now, why is it so difficult to grow gallium nitride? Let me take you to this technical part of it. What is there? Let me sort of start some sort of the discussion on the growth. All right. So if you want to buy this gallium arsenide substrate, which is the first semiconductor or early day semiconductor which was man-made, yeah. So today we get a 4-inch single crystal gallium arsenide substrate, cost around $50 to $100 somewhere. Now, if you just look at, is there something available for gallium nitride or not? You don't find anything. So what we do, or what is done, is usually, so because we can't grow, I'll talk about that little later, that single crystal gallium nitride. So we use some foreign substrate, different substrate material to grow gallium nitride, thick gallium nitride layer. So that substrate is still sapphire. Now if you look at a sapphire, so sapphire would cost like $100. This is like a 4-inch sapphire. Now on that sapphire substrate, if you add some sort of a 4 micron, less than 4 micron or 2 micron gallium nitride layer, and that cost goes to almost 10 times. Okay, so that's the value, for example. And now, so the single crystal aluminum nitride, you think about it. So this aluminum nitride, gallium nitride, there are same series of material. So if you have to only 30 to 50 nanometer aluminum nitride single crystal layer, if you place on sapphire, that cost goes to almost like $1,000. And the technology has sort of reached to a state where we can grow the single crystal gallium nitride. I'll talk about that little later, why it's so difficult. Is basically we can grow a tiny crystal. This is, you see, the 10 mm by 10 mm, 1 centimeter by 1 centimeter single crystal gallium nitride wafer, and that cost almost $350. Think about this. Now you know that what is the challenge. This is this today's price, for example. So the challenge is still there, but then you need a solution. All right. So here is another one. Like if we have to, I mean, you can make a business out of it immediately. You see here, see it's 4-inch gallium nitride crystal, gallium arsenide substrate costs $70, and then this is 2-inch gallium nitride substrate cost $5,400. So that's the kind of the value it adds to the market if we can make these gallium nitride crystals today. Now let's look at why is it so difficult. Now from a crystal growth is a material growth, right? So for example, when a material grows, two things happen. First thing is this thermodynamics. viability. Thermodynamics tells us a process should happen or not. No, the reaction, for example, or the bonding or any process, for example. Things are stable because we are thermodynamically stable. Yeah, nothing happens. Now, if we have to grow something, then we have to make it little bit of thermodynamic instable state, in equilibrium state. So here is the beauty about this gallium arsenide and why it is formed. Now, when you make the two material together, there are three things actually. One is that the bonding between this individual element itself. Let's say we talk about gallium arsenide. So the gallium, you don't you don't use single gallium. You have this large number of gallium atom. So there is this attraction between the gallium atom. And then on the other hand, you have this arsenic. Now, the beauty about this system is that the gallium bonding is much weaker, or even arsenic bonding is much weaker than gallium arsenic bonding. And that is reflected. This is something called the phase diagram. We always sort of refer to the phase diagram. This phase diagram will tell us that what conditions we'll have to keep in order to grow, make the single crystal gallium arsenide. Yeah. So you see, the gallium melting temperature is 29 degrees centigrade. Arsenic doesn't melt, it sublimates around 650 degree, it becomes gas. But if you make the gallium and arsenide exactly 50-50, the melting temperature goes 1238 degrees centigrade, which is extremely high. So that is why gallium arsenide is so stable. All you have to do is to make sure the gallium and arsenic actually at 50-50%, not less than or more than, then there is a problem. Okay. Now let's look at, is there something exist for gallium nitride? No. Gallium nitride is this because the nitrogen bonding is one of the strongest in the nature. Nitrogen gas we consider to be an inert gas. There is triple bond between the two nitrogen atoms. So you have to break this nitrogen bond and then eventually make this bond with the gallium. It doesn't happen in the normal conditions. So there are some phase diagram or process conditions which exist where we'll tell that if we can keep this condition, then you might actually grow the gallium arsenide and gallium nitride, and but that condition require extremely high pressure. You see that 50 kilobar, 1 bar is the atmospheric pressure, by the way. So 93 bar. So that's the condition. This is why getting a single crystal gallium nitride, the way typically the single crystal is grown, doesn't happen for gallium nitride. So what we do a process which is far away from thermodynamic equilibrium. Now, what is thermodynamic equilibrium? Let's say you are talking about the simple thing. How is this ice or water transformed to ice? It's a single crystal formation. So water transforming to a solid. What has to be done? The 0 degree centigrade water is stable. Ice is also stable, right? Now you bring the temperature a little bit below the 0. So you create a non-equilibrium situation. And so that temperature, the solid form of the water is actually stable form. That's why the transformation happened. And you see, you find a very nice single crystal. Same thing or similar thing happens in the single crystal growth. Take the silicon, say gallium arsenide, for example, but that doesn't happen here. So what we do, for a nitride, we create a situation which is far away from thermodynamic equilibrium. For example, a thin film deposition growth systems, which I'll talk about a little later. Now, with this the complicated sort of material chemistry, so even if you grow, or even if you have succeeded growing the gallium the gallium nitride crystals on a foreign substrate, there are many things have to be sort of satisfied. Now that is where we talk about the epitaxy. Now epitaxy is what? Epitaxy is growing a single crystal layer on a single crystal substrate. That is typically what epitaxy means. Now, in order to do that, it's basically you need to have a lot of 3 primary conditions to be satisfied. One is that you are building a block on another block. There should be some structural coherence, which we call the lattice mismatch or lattice matching. That's one has to happen. Then what is the second thing, which is in fact more important, is this whether the surface is able to accommodate that layer or not. That is driven by the energy of the surface. The surface energy compatibility has to happen. That means if we have a surface which surface energy is less than the surface energy of the layer, then the layer doesn't wet. You will have the bubble formations that you see sometimes the air droplet, the water droplet, and sometimes you see the surface which actually completely wet. This is driven by surface tensions or surface energy, for example. Now that has to happen. The third important thing, which was also very important, is the symmetry, the structural coherence. That was said another thing, that symmetrically also it has to be compatible. You can't grow a 3-fold symmetry structure on a 4-fold symmetry structure substrate. So that's why in this case sapphire is the first this substrate which was used, because they've had this similar structure. Now even we figure it out, then getting this lattice matching is extremely difficult job. So that's, if we don't have a lattice matching, then you have this kind of a dislocation on thread dislocation, which was basically driven by the relaxations of due to the lattice strain, right? Now let's look at, this is what is the structure of gallium nitride. Then you talk about the compositions. So for example, this is what we call the compound. That is exactly what happens for the gallium arsenide, but for the gallium nitride it doesn't happen here. Yeah, so it's something here. So because of the size, the difference of the size of the crystal, now gallium nitride is this alone one system, then we have to add indium into the systems or aluminum into the systems in order to reduce or increase the band gap. So the LEDs are made with the quantum well. So if you have to make a quantum well, you need a barrier and then you have a potential well. So then you need a 2 material system. So in this case, indium is added in order to decrease the band gap, for example, so that this light emission, so the wavelength increases. So that is one of the problem in this case. Now here is the lattice mismatch. You have with an aluminum nitride substrate itself, aluminum nitride or aluminum oxide, which is sapphire, 36%, 33%. The best substrate is basically silicon carbide, which is very expensive, of course. And then, so what we try to use some way to mitigate the strain intermediate between the sapphire and the gallium nitride via the aluminum nitride, which is used at the interface between the layer and the substrate. For example, this is what one of the Nobel laureates figured out. Hiroshi Yamano figured out, if you place the aluminum nitride between gallium nitride and sapphire, your quality of the layer gallium nitride improves significantly. In fact, Nobel talk about how to introduce aluminum nitride on sapphire to get this better quality gallium nitride. Now what are the process technology? So this is basically the industrially used very high throughput MOCVD system, but the lab scale we use this the MB molecular beam epitaxy, which is there at the Department of Electrical Engineering. So one of the advantages I'll talk about primarily about the MB is that we have some kind of a techniques to see what goes on at the very early stage of the growth. For example, from the very early stage, even few atom comes on the substrate, we should be able to see. Yeah, that gives us the leverage over the MOCVD to create a fine structure. Okay, so that's basically we have something called the reflection high energy electron diffractions, REED. Okay, so that the diffraction gives you this periodicity, the ordering, and the reflection would give you so the layer, how the layer is growing, for example. No, because this REED, I'll tell you why. The REED use this electron beam, and electron beam, the electron requires very sort of a clean conditions. So your scattering goes so high, then that you will not be able to sort of sustain this electron beam at very high atmosphere, very high pressure where the MOCVD works. Okay, so that's one of the, all right. So the typical heterostructures, for example, this is one example of the REED image that we see when we grow the gallium nitrides on sapphire, or the GAN template on sapphire we grow. So you see here, if you just look at the intensity scan and you see such kind of the information, and this information tells us that we have 1 or half a monolayer excess gallium than the nitrogen on the surface. This is what I'm talking about. This fine tuning is required. So we know exactly what goes on, whether the surface is gallium rich or nitrogen rich. If you have a more nitrogen surface, it will look different than the gallium. So with this understanding, these are these conditions. For example, when you talk about the two-dimensional layer formations or two-dimensional layer which is required for all electronic devices, we use such kind of growth condition. Now I'll take you through the other the implications of that. So even if you see that it is looking two-dimensional, but if you look at the inside structure, it is full of defects. And how do you do that? How do you figure it out? If you do the optical emission spectrum from this structure, you will see, for example, there is another additional peak in addition to the actual peak of gallium nitride, which we call the yellow luminescence or yellow peak, and that is a signature of huge defect that we see here. Now that is where this another thing comes in, or the structural reformation takes place. So if you now grow or make this structure large area planar to the one-dimensional nanowire kind of structure, and you see that vanishes completely. So these structures are one-dimensional, defect-free, much efficient in terms of the optical emission. Okay, now we want to look at it. So this is the conditions we can actually do just by changing the process condition. No catalyst, no additional layer depositions. It just by changing the process conditions, we can move from two-dimensional 2D layer to the one-dimensional structures or one-dimensional nanowire, which we call. Now figure, if you just look at these growth kinetics, you find out window where you will be able to grow 2D layer or sometime 1D layer. Now with that, I want to move you quickly to the actual title for examples to look at how we can sort of manipulate the growth conditions to come up with the ultra small or single photon emitter. All right. So again, I'll just say, because of these one-dimensional structures, you have more flexibility to add more atom, because you are talking about the small length scale, a more ternary system. So here in an examples of the high brightness, the green LED, which has been a problem for 3-nitride system, which is called the green gap. All right. So you see, that's all the structural reformations which has happened, and then with this you can sort of grow you can make an LED which emits the UV, of course, just the gallium nitrides, and then green, yellow, red, all these combinations that you can make just by using this 3-nitride system. Now here is this, quickly I will take. So how do you sort of first of all characterize this? Let me just quickly go to the, otherwise it's becoming difficult when I show the result. So you have this emitter here, and so let's say this is your emitter, and then this light or that comes out of the emitter, for example, or the photon that comes out of the emitter goes through the two detector. Now, and then eventually there is a correlations. You make these correlations of these photons at here, and then you see what happens. Now, if you have a single photon source, right, that means that photons, the source emitting photons once at a time. Now at t equal to 0, you have only one photon. So then correlation factors for the second order correlations that you see here, it should show at t equal to ideally at t equal to 0 at 0, for example. So that is the signature of single photon source ideally. So the statistically or probabilistically, if you look at it, if it is less than 0.5, then it's a sort of a single photon source. Let's look at how did you achieve that. What is so there are early studies just by buying. Now the ideal conditions, or the atom is actually close to an ideal single photon source. What you need in order to have a single photon source or the photon one photon emissions at a time, you have the discrete energy levels. Now in the solid state, so we talk about the band gap, we talk about the band of energy. So if you have a band of energy, for example, or the large number of density of states, it's very unlikely that you create one photon at a time. You will have a much larger number of photons. So criteria is to have a sort of an atom-like structure. That's the best thing. Now how do you create? You create something we call the quantum dot. Now how do you create the quantum dot? By using the growth, for examples, or manipulating the growth kinetics that I'm going to show you here. So there are some early studies, but you see that even in this case, even at low temperature, this is not clean single photon source. Your G2 correlation is 0.6, that's higher than 0.5. Yeah. So that's like a little bit recent studies which was used to create. At first, the challenge is to create this single photon or the quantum dot like structure or the atom like structure. Yeah. So I'll tell you what is the challenge here. Challenge here is this. So when you grow, let's say you want to have this potential well. So you have this energy barrier and in between a potential belt. So you have a two material system. Now you have a base layer, which is, let's say, the barrier, and then you want to grow the gallium or a gallium nitride crystals onto that. Now, as I said, that it is driven by the surface energy. So it's very difficult to grow a little bubble or something called the true quantum dot, 3D confined dot on aluminum nitrides or something in a large bandgap system. So typically it turns out to be like this. Now what happens? You have this dimensional confinement, but then lateral confinement doesn't exist in this case. This is what is the challenge, right? If you just typically the way this goes. Now what we did here is that we tried to make this our initial structures as already 3D or laterally confined. So this nanowire plays a very, very interesting sort of decomposition mechanisms. You know, if you just grow the nanowire and then try to decompose it at a certain conditions, you will see these decomposition happen from the edges of the nanowire. They have the 6-pole symmetry, and through the edges this decomposition happens. Now if you just study that, you can eventually make this tiny tip of the nanowire on a large diameter of the nanowire. This is what our study talk about, for example. So if you see here, these are grown nanowire. Now after some time, after a decomposition at a certain process condition, these nanowire even transfer to a tiny quantum nanowire. We call them a quantum because they are structurally very small. Like, you know, to be precise, one has to have a structure which is less than what we call the excitonic Bohr radius, right? So then it's sort of a true to call the, now if we have a quantum, the size reductions, then you have a band gap increase, for example, that you see the confinement in this case. The next slide, yeah. Now, once you have this tiny small quantum dot and this the tiny small sort of, you know, the structure which is basically confined within a small surroundings, then you are already laterally confined. Now, our concern one was only to confirm lateral or only to have the lateral confinement. Vertically, though, you can do whenever you want. Now, if you place this quantum dot on the tip of this small tiny nanowire, and then you see that you will see the emissions are only happening or coming only from the tip of the nanowire, if you can really sort of place them on the tip. Yeah, so that shows that the kind of precision that we can engage during the growth of the nanowire. You see here, now these quantum dots, for example, placed on the tip of the nanowire are essentially a true single photon emitter that I'm going to show you in the next slide. Okay, so there are two ways we have done. One is that we sort of, you see, this is kind of a, can be called a disk, for example. It's not even dot, but here you see here, when we have this, the lateral confinement already, then it is like a dot, and these are like a disk. Yeah. Now, so if you look at the dynamics of the photon emissions, the emission, for examples, from this, the quantum dot, for example, which has a lateral confinement already, are much faster than the disk that you saw before. See, this is the final figure that talks about the purity of your single photon emission or single photon emitter. So you see that the very striking thing. Now we have taken the two different kind of sample. One is this disk, another one is essentially a dot, right? Now, if you look at the G2 correlation, which is 0.1, and that comes from the dot, and then this is even the disk, which was already not so sort of greatly confined laterally, also shows the G2 correlation, which is less than 0.5. That means in both cases, you have a very sort of high spectral purity, for example. Now you see here the report, earlier report. So all that report that you see earlier are done mostly at very low temperature, 4K, the 5K, 10K, 100K. And this is the first report that we showed, or we demonstrated that even at room temperature, you will be able to create the single photon emitter if you can actually structurally make them the real quantum dot or 3D confined structures. Okay, so with that I want to stop it here, but before I sort of say thank you, so I want to show you something very interesting or useful. Now this is what is very important thing I want to show you for a student particularly. If you look at the market comparisons, we traditionally come from 3-5 other silicon germaniums. We're talking about high density memory, we're talking about neuromorphic memory technologies, and all that looks very fantastic. But look at the market position, where we are heading now. So if you look, this is on the left side, you have like a group 4, this silicon, germanium, and device market where we are. So in 5 years down the line or 4 years down the line, that is going to be $18.3 billion market, silicon germanium. Now look at on the right side, it's a compound semiconductor mostly driven by gallium nitride, gallium arsenide, silicon carbide bit, yeah. And you see here, today is 110 or $112 billion, and it's 186 or kind of $200 billion is going to go in next few years time. Now in Indian market particularly, we have a huge consumer than the world consumer today here. So our market would go from 48 billion to 86 billion with a CAGR of 10.2%. Yeah, so that's the compound. But what is this? What is the fate, or what is this funny thing here? None of these chip that we are sort of using is manufactured here. All comes from China. All come from China. So you see, during this COVID time, the import from China was significantly dropped, but the import from Vietnam, Thailand was significantly enhanced, and the China's export was mostly to this country of Vietnam and Thailand and those areas. And then you realize that it was actually coming via Thailand or Vietnam. So this is what is the fact, right? Unless we start working on it, there is no growth facility. We don't grow it here. Any compound semiconductor we use in the university scale, we do some university small scale growth, but no industry growth. Okay, so this is going to be a problem. Now we realize that we need to spend significant amount of sort of investment in making this 28 or 45 nanometer technology, for example, or silicon germanium. But this will going to come. This is what it's very important. So our Indian LED lighting market, to our values in 5 billion in 2024, a couple of years back, and it's going to go almost like a 26 or 27 billion, just the LED market itself, yeah, with the 20% CAGR, yeah. But the thing is, all of this LED chip come from outside, nothing, yeah. So with that, I want you to think about which way you want to take your career. And if you want to make a business, or you want to study fundamental, or you want to do so, this nitride can offer you n number of possibilities. Yeah, starting from the business to the fundamental studies to the quantum technologies, everywhere. Okay, with that, I want to stop you here, and thank you. And if you have any questions, comments.
Thank you, Apurba, for your overview. We have time for a couple of.
Yeah.
Can you say that quantum dot and
Acha. Yeah. Sorry that I had to rush there because. Okay, let me first start from the schematic. So, we studied that for examples, the decompositions of the nanowire, because you can't grow the quantum wire on the first shot. So if you grow it, become nanowire. What do we mean by the nanowire is diameter are 50 to 100 nanometer diameter, but those are not quantum wires. So we need this lateral confinement, and for lateral confinement for gallium nitride is around below 10 nanometer. Yeah, that is something like exciton Bohr radius. I'm talking about 6 to 7 nanometer. Now, but then if we sort of take this nanowire and then heat it up at a certain condition, very high temperature, with a nitrogen plasma environment that we have, then this convert this nanowire to a tiny sort of quantum wire. This is now, and that decomposition happens actually from the tip of the nanowire. Now, if you somehow block the tip of the nanowire with something that would not evaporate at that temperature, then the nanowire remains the same. Okay. Now, here is this beauty. So you see here, we have grown this nanowire, and then the surface is covered. The tip of the nanowire is covered with aluminum nitride. This is our gallium nitride. The aluminum nitride is much stronger, for example. It doesn't decompose at that temperature where the gallium nitride decomposes. Now, so you stop the decomposition of the ground or the bottom nanowire, and then on the tip of this aluminum nitride, so again you grow nanowire, and then that nanowire decomposes. And so if we decompose that nanowire, is eventually you form some kind of the tiny quantum wire. And then in the top you put the indium gallium nitride, which is a quantum dot. This is a critical thing, because your best structure is ready, because that already has a lateral confinement. and then whatever you put, it would be something like within this dimension itself. And then you cover up again this tiny thing with the aluminum nitride. Then you have an aluminum nitride, or let's say you want to make this the visible range. That means quantum dot is made of the indium gallium nitride, which has, let's say, the band gap of 2.2, and then that could be surrounded by gallium nitride 3.4. So you have a beautiful quantum confined 3D confined quantum structure or quantum dot. That's the way we make it. Yeah.
Okay.
Yeah.
Okay. Maybe the last question. Yeah.
So you told that there's aluminum nitride, gallium nitride, and you try to pick it up. So what exactly was the reason that the gallium nitride was not like holding on to the aluminum?
Gallium nitride was holding there. It is actually, this is why aluminum nitride wets the gallium nitride aluminum nitride surface. So the aluminum nitride surface has a higher surface energy, or the surface energy compatible, to make sure this, when you put the gallium nitride, it actually form a two-dimensional gallium nitride. And that is the problem of making this quantum dot. So we need a 3D confined. So if we have a dot kind of a structure, that is what would be best for a quantum dot. But it is not. It's actually formed this way. Yeah. So we have to avoid this. That is why.
On the last slide, I had a question that if you can just for the
yeah.
whole last this one. So in India, why can't we just import the technology and start using it? What exactly is possible?
That's what we are doing. That is what I'm trying to sort of tell everyone, that we should start investing to start. So there's some policymakers here.
Okay.
No, I mean, it is like that. It's changing very rapidly, right? This is what I'm saying, that if you take it up, if you invest your time, then there's a better future.
The Indian government's ISM policy currently does support compound semiconductor. Obviously, these are if you look at countries, they are starting with the silicon carbide, because gallium nitride also definitely.
Yeah. So this ISM 2.0 actually has 3,500 crore sort of budget for micro LEDs, which is primarily by the gallium nitride torsilated kind of structure. And I think Professor Mahapatra would also know better what's going on with this ISM. And yeah, so I talked to this ISM manager, Manish. Manish is the director, and Manish he's sort of more optimistic. But it's going to happen anyway. We can't avoid it. No, so this is going to happen. We have to take it up. Yeah. Thank you. Sorry.
Okay. Thank you, Apurba, for an excellent overview of this subject. And I think many of these discussions and opportunities can be had over tea.